Hello everyone and welcome back. Let's continue our class of foundation engineering. With this video, we will start the chapter number 3, which is about shallow foundation, ultimate bearing capacity of shallow foundation. So the two previous chapter were kind of basis for you to understand the program, to be able to handle the program. And from now on, we will start we are going in the core of the program itself, okay? From this chapter, shallow foundation, ultimate bearing capacity first, okay? This is one of the most important chapter, one of the most important part of geotechnical engineering, okay? So I hope we will learn something together, okay? So today, I will just go kind of introduction of this chapter, okay? Here is the content of this chapter. From introduction to the last point, we have 12 points in total, okay? The chapter is a little bit long because I want to give a lot of details. And as I said, this chapter is very important as it is one of the main topics in foundation engineering, even in geotechnical engineering, okay? So today we are going just to talk about the introduction, the two first points, introduction and general concept, okay? So let's start with the introduction, going to like the history of this ultimate bearing capacity, how everything started, okay? So if we check this kind of footing, then we can see the footing resting on the soil, and this is just the overburden, the surcharge, okay? The footing base level is here. What is going on when load is applied on this footing? What will go on in the soil beneath the footing? What is going on? Okay, you will see that there are a lot of sharing happening in the ground. Okay, so shallow foundation must meet two very important criteria to certify the performance. And these two are: one, safety against shear failure. As you can see here in the ground, all these arrows you are seeing are shear failure. You can see here general shear failure. There are different type of failure, of course, but the main way of failure of the ground is just through shear. Ground can resist compression very much. Traction maybe no, but the main failure of footing or foundation is just through shearing, okay? Shearing. So that's why the first criterion that shallow foundation should meet is safety against shear failure, okay? So the foundation must resist overall shear failure in supporting soil. You can see here, the supporting soil is here. We don't care much about the overburden, the surcharge soil, the shearing resistance of the surcharge soil. We care about the soil that is supporting the footing. This means the soil beneath the footing, okay? It should be resistant against shearing. Number two is about settlement, okay? Because even if the shearing, safety against shearing is satisfied, settlement is another thing that is very important in shallow foundation. Not only shallow foundation, actually, it's all type of foundation. The settlement is something very important, okay? We cannot prevent settlement. I mean, we cannot say that settlement should not happen at all in foundation. That is impossible. But it should be like acceptable settlement. Okay, the amount of settlement should meet some requirement of the project. Okay, if it is excessive, okay, as you can see, the foundation should not undergo excessive displacement or settlement. Okay, it will depend on, as I said, specific requirement of the structure. So each project has specific requirement depending on the importance of the building. If you are building, for example, hospital, the requirement will not be same as if when you are building, for example, like a residential building, or if you are building a primary school. Okay, each project has some requirement that we have to meet. The foundation should not exceed, the settlement of the foundation should not exceed these requirements. Okay, so the load per unit area, as you can see, some people don't make difference of this. You can see here capital Q. Okay, this is kind of force, but what we want most here is load per unit area. It means like pressure, not force. Okay, the force coming, you can see this arrow is force in kilonewton, but what we need is the pressure under the footing. It means in Pascal or kilopascal. Okay, that is load per unit area. Okay, that load per unit area at which the shear failure in soil occurs is what we are calling here ultimate bearing capacity. This is the title of this chapter. Okay, ultimate bearing capacity. I mean, this is very basic explanation of everything. Okay, for some people who already understand this might be boring, but if this is the first time for you to hear the word ultimate bearing capacity of foundation, I think you will not be bored. Okay, so this is what we are going to explore in detail in this chapter. Okay, the ultimate bearing capacity. So it means this force coming here divided by the area of the footing. This is the load per unit area. Okay, and the load that will correspond to the failure of the underground, the ground beneath the footing. This is what we are calling ultimate bearing capacity. Okay, so I hope from now on, when we say ultimate bearing capacity, you will understand what we are referring to. Okay, general concept now. Number 2, that was introduction. General concept. So for strip footing, strip foundation, for example, with width of B, the larger of the footing is B, and the footing resting on dense sand, for example, or stiff cohesive soil. Okay, as we will explain this now. So the thing is, bearing capacity, ultimate bearing capacity. I hope you understand now, from now, what is ultimate bearing capacity. It depends on the type of soil. Okay, type of soil. With the same footing, I mean same dimension, you can see here B, the width of this footing, B. With the same footing, if the soil beneath the footing is different, you will have different bearing capacity. So the type of soil matters. Okay, so this figure is showing kind of like a relationship between the bearing capacity, I mean the force per unit area, which we are calling here Q. Okay, you can see here it's written load per unit area, Q. Okay, if you see capital Q, it means force. If you see this small q, it is pressure, means load per unit area. Okay, so that is here, and here is settlement. Okay, So this is the two most important criteria of bearing capacity, as we explained, right? So we put one here in horizontal axis, the settlement here in vertical axis. Okay, you can see that sometimes this vertical axis is like upward, but it doesn't matter. We just want the relationship between the Q, the bearing capacity per unit area, and the settlement. Okay, so you can see here for each type of soil, you will have a different shape, how the soil will deform under the footing. Okay, and how will be the shape of this curve, the curve of like load settlement curve. This is the name of this curve. Okay, so if you have this kind of failure happening in the ground, you will see like if you push, okay, you push the footing into the ground, you will see that something like this will happen, this kind of shape. And you will see that the shear line, this is the shear failure surface, which are these lines, they will extend up to the surface like this, see, to the surface. And you will observe some kind of heave here, okay? This kind of failure, we call them general shear failure. I already explained you that this is shearing happening in the underground beneath the footing, okay? But we may have also this kind of failure in the ground. You can see that this time, these are just like dots. So it means the failure doesn't, the failure surface doesn't reach the surface here. This line, okay? We may have also this kind of failure, this type, okay? Here, the B one is local shear failure. And this one is punching shear failure. It's like a punch, just a punch going into the ground, okay? So you can see that each type of failure, this load settlement curve, please understand load settlement curve. This is very important matter, okay? What is load settlement curve? Is this load per unit area versus settlement. Settlement means how many millimeter the footing went down, settle, okay? So this should be like in millimeter, and this one like in kilopascal or pascal, something like, okay? So in case of dense sand and stiff cohesive soil, dense sand, you already know, it's sand but very dense, okay? Not loose sand. Cohesive, stiff cohesive soil. Cohesive soil is like clay. It just another way to say stiff clay, for example, okay? Stiff, it means strong. If you have this kind of soil, you will have this kind of failure in the ground. Figure A, this kind of shear failure, see? And you will have this type of load settlement curve, okay? So if you apply, it means if you apply gradually the load on this, okay, it will result this one in this curve. It means if you are here, the load is here, the settlement is here. If you are here, the load you applied is here. Just check the coordinate of this point, okay, here. If you are here, here. Then if you watch this curve, what will be the ultimate bearing capacity? Because at the end of the day, what we are looking for is the ultimate bearing capacity and the settlement corresponding to that, okay? So the relationship between load per unit area, which is small q, means pressure, and settlement is shown here, okay, as I explained already. So I said, what is the ultimate bearing capacity? It means the ultimate pressure, ultimate load per unit area. Okay. It's said here at a very specific load, okay, we will call it QU. U here is standing for ultimate. Okay. Okay. When you reach this QU, sorry, a sudden failure occurs in the supporting soil. Okay. And the failure surface extend to the ground surface. You can see something like. So this QU is what we are calling here ultimate bearing capacity, because when the load per unit area reaches this point, a sudden failure here occurs into the ground. Okay. And you can see this kind of thing, failure happening into the extend to the surface. So this is physical meaning of ultimate bearing capacity. Okay. This load referred to as the ultimate bearing capacity, as I said, represent the maximum load per unit area the soil can support. You can see that there is no load. After here, the load is not going in this direction anymore. It's going this. It means if you go small, the settlement is now very large. Okay. The maximum load you can see here, the maximum of this curve is this one. This is the ultimate bearing capacity. Okay. Maximum load per unit area that the soil can support. The soil beneath the foundation, the footing can support. Okay. So when such failure is sometimes abrupt and extensive, it is termed general shear failure. So this is what we say here, general shear failure. Now, if we go, the previous case was in case of dense sand and stiff cohesive soil, right? If you remember. Now, if we go to like medium sand, medium compacted sand, it means our sand is not very dense. It's not dense. It's like a medium, because you have loose sand, medium sand, and dense sand, right? In the previous one, the A was for dense sand. Now we are going for medium sand. Okay, medium compacted sand and clay soil. If you have this kind of soil, the load settlement you will obtain, load settlement curve you will obtain will be something like this. And it is something like this one. You will obtain as type of failure into the ground. So if you increase the load will cause, of course, settlement with failure surface gradually extending outward. Okay, gradually. Okay. The reason for this is very simple. Actually, when you are pushing, the force you are using to push is kind of like densifying the soil, because there is still room for densification. But here it was already dense, maybe maximum dense. It cannot be densified more. So if you push, you force it to densify, it just like suddenly collapsed. But here we said medium compacted sand. Okay, it means the sand is dense, like compacted, but it's not like 100% compacted. Like the compaction is not. There is still room for compaction. Okay, so that's why if you push, the footing is compacting a little bit, and you will see the curve is going like this, kind of like this, increasing, like it's not like this. Okay, it is like you are going to make the soil to become this state. So the most important thing for you to remember is that if you are dealing with medium compacted soil, the failure will be like this. Okay, very important. So at certain load, which we are calling here Q, known as first failure load, Q1, this one actually, okay? We maybe change this. The first failure, the first failure load, we have this kind of behavior of the foundation, okay? This a sudden jerk. So that we write down this kind of load. You can see that this is linear, but right after that, you can see that the curve is not linear like that. It is a little bit changing the direction. See, it was going like this. If it continue in the same way, it should be like this, right? But here it suddenly changed a little bit the direction. Okay. We note that this one, QU1, ultimate one. Okay. Then if you add more load, additional load lead to now considerable movement before the failure surface reach the ground surface. Okay. So at that time, we will now have our ultimate bearing capacity. Okay. It means you continue. If you're here, the direction changes, and you continue adding load, and you will obtain now, you will reach another change of direction like this. And this is where you reach the ultimate bearing capacity, and the shear failure will reach the surface. Okay. So as I said, this is just because there is still room for densification, for compaction of the soil. So you will compact it first, okay? And after that, you will eventually reach this state somehow. This is the meaning. So then you will call this the ultimate bearing capacity. But it is not this one. This one is just, we said, first failure load. Okay. So let's continue. So this one is what we call here local shear failure. Okay. This one was general shear failure. Okay. So unlike this, the general shear failure, this local one, the local shear failure one, does not show a clear peak of load. Here we can see the peak of load clearly, but this one, there is no clear peak of load. Okay. And the settlement will increase, like there is a considerable increasing of settlement if the load is high. Okay. Let me change this. This should be here. You maybe one, kinda. Okay, anyway, I think it's clear for everyone. Okay, let's continue. So we are going now for loose. Of course, this is like dense, medium dense, and now loose. Okay, for loose, it kind of like there is room for densification, but the room for densification is too big, so that the footing itself is going like a punch directly. The soil is too loose, so the footing itself is going directly inside, punching inside. Okay, so if you have foundation on loose soil, this one, the load settlement curve, it is like this. Okay, no failure surface extending to the ground this time, because before you reach that, all the footing will go inside. Okay, so the failure will be like this. failure surface. But in all each line you see here, sharing is happening around each line here. Sharing is happening. So beyond the ultimate load failure, okay, ultimate failure load, the curves becomes like steep and nearly linear. Okay, beyond this curve becoming maybe linear like this. We can see that this curve is maybe similar to this one a little bit. Can see, right? So you can see that the curve is curved. The beginning, it's not linear like this one. This one was linear, very linear. But here it just curved. And from here, you will see that it start to be linear, almost linear now. Okay, so the where this started to be linear, this is where we get our ultimate load capacity, bearing capacity. Okay, so that is what he said here, ultimate failure load. Beyond that, the curve becomes like nearly linear. That indicate significant settlement with little increase of load. If you increase load just a little bit, like from here, we are here, and here, you can see that the load is small, increase, then you have large settlement. Yeah, then you can say, you have reached your ultimate capacity. So this is what we are calling here, I said, punching shear failure. Punching. Okay. So I will put the three cases. Okay. Dense, medium dense, and loose soil. Okay. So this is a study investigating. You can see here density, dry unit weight. Okay. Unit weight divided by unit weight of water. This is here, the horizontal line. And here is like a relative density. Okay. Relative density is, I think we have talked about this before. This is what is um what is the indicator of the density of your sand, to say of your soil, if it is dense, loose, or medium dense. Okay. In the first chapter, we have talked about this, and we have seen what is the value, what is the range value of relative density corresponding to each type of each state of densification of soil. Okay. For dense sand, the value of the range of relative density is given for medium sand and loose sand. Okay, please remember that. So this study, this is just kind of like a bearing capacity, the ultimate bearing capacity. The first one, as you see, the first one and the ultimate one, which are normalized by gamma and B. Gamma is maybe the unit weight, and B is the larger of your footing. Okay, normalized. But we can agree to say that this is just bearing capacity. Okay, so this study is giving, you can see this first line. This line is the ultimate bearing capacity, and this dash line, the continuous line is Q. Okay, normalized by this. The second line, dash one is the line is Q1. Okay, so it shows you here where the punching shear failure happen, the limit of density. Okay, this is in sand, only sand, and you will see later why we normalize this by this, because this is about the bearing capacity. This is in the formula of bearing capacity, which we will see later. Okay, local failure happen in this range. of relative density, if you want. And general failure happen in this range of relative density, okay? But anyway, the person who did this study was Fasick in 1963, okay? He just performed lab study, load bearing test. It was on circular footing, okay? That's why it is better to normalize by B, because if you normalize that, it means the effect of the footing larger is kind of eliminated. Okay, it was circular and rectangular plate supported by sand, and the sand were like with various relative density of compaction, as you can see here, various relative density. So what he did, changing the relative density, and the result, I already explained the result, okay? And you can see here, these dots, square, dark one, are like circular, and the dimension is here, 203 millimeter. Okay, rectangle, square again, but white is same circular, but the plate is smaller. Okay, so by normalizing, you will remove the effect of the B width. Is the circular one, dark circular one, is a circular plate with this dimension, and white circular one, we have circular plate with this dimension. And these dots are like a triangle one, a rectangular plate with this dimension. Okay, but we can obtain these trends. Very interesting. And we test, it shows that for relative density around 70%, the soil will exhibit a general shear failure. You can see here, around here, 70%. Please, if you forgot what is relative density, go back in chapter 1. I don't remember which video, but it is there. Relative density, and there is range of the definition of relative density is given. You can use E minimum, E maximum to calculate relative density, or you can use just the density, rho mean, rho max. So anyway, around 70%, you will have this general shear failure. So on the basis of experiment, basic again, basic like 1973, proposed a relationship for mode of bearing capacity failure, like failure mode of footing, which is shown here. Okay, you can see here, this is relative density, and this one is the depths, D, you can see DF, the depth of footing from the ground surface to the base of the footing, which is normalized by B. B is here, width of the footing. So it's showing which area, in which zone you will have punching shear failure, local shear failure, general shear failure. Okay, so it means the relative density is not the only factor affecting the type of failure, but the depth also is another factor that you have to consider. As you can see, for example, if I take relative density of, I will say even 8, 0.8, okay? If I am at depth 1 meter, the ratio, depth ratio of 1, I will be like in here, general shear failure, okay? General shear failure. But if I go up to 4 meter, for example, 4, the ratio of depth ratio 4, it will be like local shear failure, something like that. Okay, because if it is too much deep, the shear surface, the shearing surface, the line cannot reach the surface. Okay, if the footing is too deep, like here, you remember what is general shear failure? The shearing line are going up to the surface. If it is too deep, it cannot go up there. That is the problem. I will go back to show you what I'm talking about. You can see the general shear failure, these lines are going up, like this, up. But if it is too deep, this footing is too deep, it cannot reach up easily. So it will be around here or even here. This type of failure or this type of failure will happen. That's the problem when it is too deep. So it means if you have this ratio, which is like more than maybe this limit, 3 point something or 4, you can be almost sure that you will not have general shear failure. It will be either this local one or punching one. Okay, so but remember that there are some norms about the definition, even the definition of shallow foundation. This ratio, for in the case of definition of Terzaghi, we will see later, this ratio should be like 1, maximum 1. It should be here. Okay, there are some limit depending on each country. The definition of shallow foundation. Okay, if the depth is larger than, maybe this ratio is more than 1 or 2, it is not shallow foundation anymore, right? But this depends on each country. Okay, so this figure involve this kind of thing. Relative density, as I said, depth of foundation measured from the ground surface, and B, this B star, you can see here, B star is this formula actually. 2 multiplied by B is the width of the footing, L is the length, the larger of the length of the footing, okay? B is larger of the footing. So this is explained here, width of the foundation, length of the foundation, okay? But L is always larger than B, of course. Otherwise, it will be inverse. So in case of square footing, you will have B and L same because it is square. In circular footing, B is equal to L is equal to the diameter. Okay, in that case, this B star will be equal to the diameter equal B. Okay, this figure is presenting settlement. This figure is presenting settlement of circular and rectangular plate on sand at ultimate load. Okay, the settlement S bar B. This means the settlement was normalized by the footing width, the larger of the footing. Okay, and here we have here relative density. Because this is similar, you can see it's similar like to the study that made a relationship between relative density and the type of failure. Okay, and the bearing capacity, we can say. But here we have settlement and type of failure and relative density. Okay, so you can see something like this kind of curve. Okay, circular plate, this is circular, and this one continuous line is rectangular footing. So depending on the type the result is showing that for shallow foundation, if this is small, the relative depth is small, the ultimate load typically correspond to the settlement range from 4% to 10% of B. Okay, because this is percentage 0, 5, 10. So the ultimate capacity correspond to this settlement 4% to 10%. Okay, if we are under general shear failure is here. Okay, so if you go general shear failure, you can see that it is here. This is 5, right? 4 is just around here. To 10%. This is in case of general shear failure. Okay. But if you go, for example, local shear failure, which is this range from here to here, cut this part. So this area, this zone, this area. Okay. Then we have what percentage do we have? It is 15, okay, to 25. Between these two, 15 to 25. So you understand now the importance of type of failure in case of like shallow foundation. Okay. Shallow foundation means this ratio is small. So if you are in case of shear failure, general shear failure, then the bearing capacity, the settlement corresponding to the ultimate capacity is between 4% to 10% here, between this range. Okay. So if your foundation is on dense sand, dense soil, which correspond to shallow, to general shear failure, then you can assume that the ultimate bearing capacity is obtained when the settlement, you understand what is settlement, right? Is when the settlement, the footing is going down, this is settlement, is around 4 to 10%. People generally consider 10%, okay? 10%. But if you are in case of local shear failure, it goes up to 15 to 25% of the percentage is against the, like the B, the width of the footing. Okay. Okay. This was like an introduction of this chapter. From next video, we will start like doing, bringing up the formula, equations that give us a ultimate bearing capacity of footing. Okay. So thank you very much for your time, and see you next time. Thank you for your time.